Hello everyone, welcome to the fourth lecture of the P block series. And in this video, we will be covering the 16th group of the periodic table for your JEE Mains or NEET. Keep in mind that I am covering only the NCERT portion which is relevant to your syllabus, and this is not even close to being enough for advanced. So, you will have to refer to JDLE or perhaps other teachers for that. Yeah, that's not my field of expertise, so let's just go on. So let's begin with the group 16 elements. What are the group 16 elements? The group 16 elements are oxygen, sulfur, selenium, tellurium, and polonium. This group is known as chalcogen or chalcogen, whatever you want to call it. This is chalcogen, group 16. Remember that. They can ask you in a question, or perhaps they will use the word chalcogen in a question. You should know that it refers to group 16 elements. And well, let's start about occurrence then. Occurrence or abundancy. Occurrence. Here, oxygen is most common element on our planet. What does this imply? That this basically oxygen and compounds of oxygen, they take up about 47% of the entire earth, and that is almost like half of the entire landmass of the earth. And if you don't already know, oxygen is about 21% of our atmosphere. So you can see at oxygen has a very big, you can say, control over the earth's ecosystem, because 21% of it is in the atmosphere and 47% of it exists in the landmass. So oxygen is a really important element. I mean, you should know that without me telling you, but yeah, if you have learned something new, that's great. But the abundance of group 16 elements falls as we move down from oxygen to sulfur. Sulfur is, you need not remember this, but this is only around 0.03 to 0.1% of the Earth's crust. And sulfur exists in sulfates. Like sulfates are its ores. What are ores? Like maybe gypsum or Epsom salt. I don't know if you need to remember this, but you cannot trust our beloved agency, so I would appreciate it if you remember the names of these ores. Gypsum, Epsom salt, and barite. These are, gypsum is basically calcium sulfate with 2 waters of crystallization. Epsom salt is magnesium sulfate with 7 waters of crystallization. And barite is just BaSO4 with no waters of crystallization. In salt analysis, you are going to read a test which is called Barita water test. Like you will study this in advanced level salt analysis, and it uses, I think it uses BaSO4, but I am not sure. So just, you don't have to remember what I said. And if we talk about sulfur once again, it not only exists as sulfates, like these are its sulfators. It can also exist as sulfides. Like sulfide is the ion which is basically just the sulfur atom with a -2 charge on it. So this is a sulfide ion. In a very general thing, you can remember that nitride, sulfide, oxide. You can just remember this as it is the base atom with their negative group valency on it. So this is called, it is the meaning of the suffix "ide". Like this is nitride, sulfide, this is oxide, and they also present others like carbide, fluoride, and so on. Now let's talk about what kind of sulfides can you find sulfur in. You can find it in, we also studied this in group 14 elements, that the ore of lead is galena. Galena, which is PBS. Galena is also an ore for lead and also an ore for sulfur. So it's a multi-purpose ore. Isn't that nice? And there's zinc blende. Zinc blende, like it's blend with an E. So zinc blende is basically ZNS. These were the sulfide ores. And one last ore I want you to remember is copper pyrite. Copper pyrite is CuFeS2, CuFeS2. So these are all the ores for sulfurs which are there. It is not necessary to remember all of this, but it can give you an edge because we never know. So yeah, let's now talk about their electronic configuration. Electronic configuration is Ns2, Np4, and they have 6 valence electrons in the outermost shell. Now let's talk about the most important part, which I say in every lecture, that the trends. What are the trends of group 16 elements? Well, the first trend I obviously want you to know is atomic radii. The atomic radii, it increases as you go from top to bottom. Why does it increase? If you don't know by this point, you can leave chemistry, but atomic radii increases top to bottom because of increase in the principal quantum number n. If number of shells increases, of this is a nucleus. If number of shells increases, of course the radius of the net atom will increase, and top to bottom it increases the number of shells. So of course radius increases as well. And the NCERT mentions this explicitly, that the oxygen atom is exceptionally small. I hate writing the word exceptionally, but yeah, oxygen is exceptionally small, like very small. It's incredibly small. So remember this as a fact. Maybe they can ask you which of these are exceptionally small. So now let's talk about ionization enthalpy. Ionization enthalpy is basically the energy you need to remove the electron from the outermost shell of an atom. For example, if this is an atom, this is nucleus, this is the first shell, this is the second shell, and in the second shell, one electron is just chilling. So, in order to take this electron out of the nucleus, you will have to like provide energy. So this guy comes out, and that energy to remove the outermost shell is called IE1, and its full form is ionization energy or ionization enthalpy. The ionization energy, it decreases as you go from top to bottom. Why does it decrease? Because number of shells increases. Basically the influence of the nucleus on the outermost shell, which we call as the effective nuclear charge, it decreases, and hence we need to provide lower energy to remove the outermost electron. And one another fact that the NCERT mentions, that this group, yeah, or G16, has lower ionization enthalpy than G15. Why is that? I have explained this in last lecture as well, but let me just repeat for the first timers. They basically say we are talking about only corresponding group 15 and group 16 elements, so they have an inner core X. We are not going to talk about X. Just we need to know that the outermost shell configuration is NS2, NP3 for a group 15 element. And for a group 16 element, the outermost configuration is NS2 and P4. So, as you know, nature, even down to the atomic level, appreciates a sense of symmetry. So, since the p orbital can hold, like the p orbital looks like this on paper, so it can hold 6 electrons. But if we only give it 3 electrons, according to I think Hunt's rule of maximum multiplicity, it all of those electrons will take up one p orbital, and this gives a sense of symmetry to the compound, and hence it becomes more stable. Symmetry causes stability, and which is why if something is more stable, you will have to provide more energy in order to cause that stability to break. So this is why group 15 elements have higher ionization enthalpy, because it you need to provide more energy in order to break the stability which is given by this half filled piece of shell. And if we talk about group 16, if I remove one electron from the outermost shell, this will become a np3 configuration, which is it reaches half filled state. So it just becomes easier to remove this electron, because the product, basically the product of our phenomena, that becomes more stable because of the attenuation of the half filled piece of shell. So this was it about ionization enthalpy of the group 16 elements. Let's now talk about electron gain and electron gain enthalpy. What is electron gain enthalpy? It is basically the opposite of ionization energy. Electron gain and enthalpy is the energy released or absorbed whenever you have to add an electron to the basically the core of the atom. So if this is an atom, this is nuclei, this is a shell, this is another shell. Now say you want to add another electron to this guy. So in order to do that, you will have to either provide or this will release energy. So this is what is called electron gain enthalpy. Now the trend of electron gain enthalpy is little it's a little bit weird. Like, as I told you earlier, the oxygen atom is exceptionally small. So if something is small, you can look at like this is nucleus, and this is a very small atom, so the effect of the nucleus on this guy is very strong. And if you want to add another electron here, the nucleus will have a very strong effect. So wait, I explained that in a wrong way, I'm sorry, I'll repeat. If you have an electron here, if you want to add another electron, so this will face repulsions, because there's only one electron and it dominates the entire space. So the electron gain and enthalpy will be very low for this. Like, the energy released from adding an electron will be low, because the result will not be that much more stable than what we had earlier. So this is why the electron gain enthalpy of oxygen is less negative. What does less negative mean? Less negative means basically it will release less energy. As you know, by thermodynamic convention, if the sign of delta H is negative, means energy is released. And if energy is released, that would mean that the resultant is more stable than the reactant. But here it is less negative, as I mentioned, because of the reason I told you. Now, after oxygen, if we go to sulfur, sulfur's electron gain enthalpy is more negative than oxygen, because sulfur is comparatively a larger atom and it has more shells. So the effect of nucleus and the inner electrons is not that pronounced, and it is easier to add an electron to sulfur, and that would easily give you more energy than oxygen. But sulfur was the element in group 16 with the most electron gain enthalpy, magnitude wise, and the most negative electron gain enthalpy. Because when you start going from sulfur to selenium to tellurium to polonium, it again starts getting less negative. Start getting less negative. So, as a fact, just remember that in group 16, sulfur has most most negative electron gain enthalpy, and hence the highest magnitude of electron gain enthalpy. Okay, now let's talk about electronegativity. Now the NCRT has two conflicting points about electronegativity. It is the average NCRT moment, as you know. Like if you go by the text, it says that with increase in atomic number, which means that from top to bottom, the electronegativity decreases, which signifies increase in metallic character. Because you know metals are electropositive and they tend to give out electrons instead of pulling them. But if you go by the table which they have shown, then it shows you that oxygen is most electronegative. Electronegative, like that isn't a surprise. Oxygen is the second most electronegative element in the entire periodic table, and after that comes sulfur. But sulfur and selenium, they are almost equal, but selenium takes the lead by just 0.04 difference, and then again this just decreases from selenium to tellurium and then to polonium. So they, in the text they say that it decreases top to bottom, but in the table they show that selenium is greater than sulfur. So I would say go by the text because they don't expect anybody to look at the table as carefully as I have done. So go by the text and the electronegativity decreases down the group. Now this was the trends that you had to remember. Now we can start talking about the physical properties. What physical properties are shown by the group 16 elements? Well, let's start with metal, non-metal as always first. Oxygen and sulfur are non-metals. I see a lot of people getting confused here that they think sulfur is a metal, but no. Sulfur is actually a non-metal. I am highlighting this because I have seen my friends and other people get confused that sulfur is metal, but no. Sulfur is a non-metal. Because make sense that you are going from top to bottom and the metallic character must increase from top to bottom. So how can sulfur be a metal? It is the second highest element in the group. But as you go down, both selenium and tellurium, they are metalloids. And the NCRT calls polonium a metal. So remember this, they are important and they are relevant, and you will definitely be asked a question about this. Now, polonium is radioactive. Don't make me explain to you what radioactivity is, but polonium is basically it decays. So it will decay into something which is more stable, and it will send out a particle. We are not diving into that. Just remember, polonium is radioactive, and its half life is 13.8 days, which means that if you have, say, on day 0, you have 50 poloniums with you. That would mean that after 13.8 days, you will have 25 polonium with you. This is what radioactivity means, or basically what the half-life means, that after 13.8 days, the concentration of polonium will half from what it was 13.8 days ago. Now, the melting point and boiling points, they increase with increase in atomic number, or basically they increase as you go from top to bottom. But again, the NCRT shows you a conflicting image here, that this is mentioned in the text that melting and boiling point increase top to bottom. But if you look at the table they have given, the melting point does actually increase from oxygen to sulfur to selenium to tellurium. But Just after tellurium, the melting point of polonium is lower than that of tellurium. And not only melting point, this is true for both melting point and boiling point. This is the data given from the table, but this is the data given in the text. So this is like, it's a contradiction from the NCERT. So you don't expect sense from this book anyway. But yeah, I would say focus on what is there in the text and not in the table. Now, another point NCERT explicitly mentions is that how do I explain the large difference in melting point and boiling point? Like, I just write difference between melting point and boiling point of oxygen and sulfur. Why is that? Like, if you look at the table, our holy grail, the melting point of oxygen is 55, that of sulfur is 393. Boiling point of oxygen is 90, but that of sulfur is 718. Like, that is a massive jump. Why is that jump happening? This happens because oxygen exists as a diatomic molecule, which is O2, but sulfur exists as a crown. Yeah, a crown, like S8. It exists as an octaatomic molecule, and its structure even looks like a crown. I forgot the structure, but there was S. This was the structure of sulfur, and it exists as this molecule, while oxygen just exists as this boring diatomic molecule. And basically, what happens is this allows sulfur to have a greater melting point because they are better packed together. So I am not writing this, Alexa. Just keep in your head. And we are done with physical properties. Let's start with chemical properties then. Chemical properties. So first let's talk about the oxidation states. What oxidation states can we expect from the group 16 elements, and what, like, there's nothing after the end. What oxidation states can we expect from the group 16 elements, the chalcogens? So basically, the negative 2 oxidation state is very common, but its stability, it decreases top to bottom. Like if you see oxygen in most of its compounds shows negative 2 oxidation state. You must have studied this in redox reactions, like unless there is a peroxy linkage like H2O2 or there is OF2, then oxygen will always show negative 2 oxidation states except for these two cases. Here the oxidation state of oxygen is negative 1, and here it is positive 2. And this is because fluorine as an element is more electronegative than oxygen. Like, it is the only element with electronegativity 4, while oxygen is 3.5, and hence it this explains why oxygen shows an oxidation state of +2 instead of -1 or -2. And keep in mind that this -1 oxidation state is not true for hydrogen peroxide. It is true for any compound where you can see a peroxy linkage. For example, if you see chromic oxide, in this compound 2, the oxidation state of this oxygen is 2, sure, negative 2, sure. But for these oxygens, all of them show the oxidation state of -1 because of this peroxy linkage. So this was the explanation for oxidation states. Now let's talk about the other elements, like for the rest of the group 16 elements. +2, +4, and +6 are quite common oxidation states. For example, SF4 exists and SF6 exists. You must have studied in chemical bonding. And but plus out of +2, +4, and +6, +4 and +6 are more common, and obviously by the inert pair effect, The stability of plus 6 oxidation state decreases top to bottom, and that of the plus 4 oxidation state increases top to bottom. Polonium, like PO, it rarely shows minus 2. Just remember this as a point. And one last thing, that sulfur, selenium, and tellurium, they show plus 6 with fluorine and plus 4 with oxygen. This was about the oxidation states. Now there is this extra paragraph on anomalous behavior of oxygen. What is anomalous? Basically, it's the weird behavior of oxygen. Like it is the odd one out. Why is that? Because of its lack of d orbitals and its small size. Like we told you, it's exceptionally small. So, what is the consequences of this weird behavior? First of all, H2O has strong H bonding. Like if you drink water, you will be able to feel the H bonds on your tongue. No, you won't. But if we talk about H2S, it does not have hydrogen bonding. Maybe it does, but not that strong. It thanks to the high electronegativity of oxygen and its small size, they are able to form H bonds like this. Like this forms with this forms with this, and it just becomes a very stable thing after all. And that is how the H bonds are formed. And once again, why is this weird oxygen character? I told you it's because of lack of d orbitals and the small size. And one thing that kind of relates with organic chemistry here is that the covalence of oxygen is limited to 4, like the rest of the second period elements, but in practice it rarely exceeds 2. Like in organic chemistry, you must have seen that in ethers, ROR dash, oxygen is happy in this state where it's forming two covalent bonds, or maybe in alcohols, ROH, again two covalent bonds. And whenever it does form a third bond, for example, whenever you protonate an alcohol like ROH, whenever an H plus comes and you protonate it, there is a tendency for oxygen that to kick out one of the atoms which are bonded to it, because it does not like being in a covalence greater than 2. So the covalence of oxygen rarely ever gets more than 2 in practice. So now let's talk about reactivity. First, let's talk about hydrogen. How do the group 16 elements react with hydrogen? Well, they form MH2. Like, that's a better way to write it is H2M. Like, you have seen H2O, H2S, H2Se is also there, H2T must also be there. So these hydrides are formed basically by the group 16 elements, and basically they are acidic. They let me write the form hydride, and they are acidic. The acidic character increases from top to bottom. Why is that? Because the structure of the hydride looks like this. No, structure of the, what am I doing? The structure of the hydride looks like this. This is the element and this is the hydrogen. Basically what happens is that when you go from top to bottom, these bonds get weaker, so it's easier for them to break and this to release as an H plus. Basically the bond dissociation energy gets low and you can easily break apart an H plus from here, and hence the acidic character increases top to bottom. Now for the same reason, the thermal stability decreases top to bottom, because of course if this bond is getting weaker it's going to break easily, and that makes the overall compound less stable. And this also explains the reducing character increases top to bottom, because it think of like it's quite intuitive if you think about it. The thermal stability is increasing, so it's decreasing top to bottom. So if something is not stable, it will try to change its state. So reducing character tries to change its state by making it a reducer. So if it reduces using its hydrogens, it is going to be a better reducing agent. Now let's talk about their reactions with oxygen. They can form compounds which look like MO2 or MO3. Like even oxygen, they can form ozone, and they can also form compounds like SO2, sulfur dioxide. They can form sulfur trioxide. They can form selenium dioxide. Now there are some extra physical properties mentioned here, that ozone and sulfur dioxide are gases. Selenium dioxide is solid. You don't need to remember this, but I have written. So the reducing agent power of dioxide, of basically MO2, it decreases top to bottom. What does this mean? This means that while SO2 primarily acts as a reducing agent, if as soon as you go to tellurium dioxide, it is suddenly an oxidizing agent. And if we talk about the EO3, like SO3 or TeO3 or SeO3, these are also formed by sulfur, selenium, and tellurium, and they are all acidic in nature. Now, that was it about oxygen. Let's talk about the halides, or basically their reactions with halogens. So, how do the group 16 elements react with halogens? They form compounds like MX2, where they have plus 2 oxidation state, MX4 with plus 4 oxidation state, or MX6 with plus 6 oxidation states. So first of all, the stability of these halides. They Fluorides are the most stable. Fluorides are more stable than chlorides, than bromides, and than iodides. This is of course because the small size of fluorine atom, they are better accommodated around the metal, and this is how the stability increases from iodine to fluorine. Now if we talk about hexahalides, which are MX6, only stable when fluorine is X. What does this mean? It means that compounds like polonium hexaiodide doesn't exist, selenium hexabromide doesn't exist. They will only exist when the halide ion is a fluoride ion. And again, I told you this is because fluorides are most stable because of the small size, and they are better accommodated around the octahedral structure. And NCERT mentions this as a separate point, that sulfur hexafluoride is exceptionally stable for steric reasons. And last point, that hexahalides are gases. Like whenever you add a hexafluoride, basically because only those exist. They are gases. Now the NCERT mentions some extra physical properties of halides, so let's just take care of those. Sulfur tetrafluoride is gas. Selenium tetrafluoride is liquid, and tellurium tetrafluoride is solid. So I guess this was it. That was the entire group 16 of the P block elements, and I hope this lecture was helpful to you. I have explained every point mentioned in the NCERT in great detail, and if you have any doubts, just let me know.